Hi everyone, my name is Nguyen. My project is a finite element analysis of an L-shaped steel bracket in ANSYS Mechanical. The goal is to find out how the radius of the inner fillet changes the peak stress, the deflection, and the factor of safety. As the picture shows, the stress is not uniform. It peaks sharply at the inner corner, and that corner is what this study is about. And here's the motivation and objective. The bracket like this transfer load around the corner, the inner corner. So that corner sees a much higher stress than the rest of the part. It is the critical location for yielding or fatigue cracking. The most direct way to control it is the fillet radius. So the objective is simple. Measure how much a larger fillet reduces the peak stress and the deflection and how much it's improved the factor of safety. And here's the model. It is an L bracket. Both legs are 100 millimeters long and the section is 8 millimeters of thick. The material is structural steel. Young's modulus is 200 gigapascal, and the Poisson's ratio is 0.3, and the yield strength of 250 megapascal, which I use for later the factor of safety. And the back face of the vertical leg is fully fixed and a 500 Newton downward force is applied at the end of the horizontal leg. The the thing the only thing I changed between cases is the inner fillet. 2, 5, 10, 15 millimeter. The work has three steps. First, an element study. I solved the same geometry with three different elements types to make sure the result does not depend on the element choice. Second, a mesh convergence study. I refine the mesh until the answer stops at changing, and I keep that converged mesh. I call it M6. Third, the main study, I solved the four fillet radii, so all on that same M6 mesh and compare the stress, deflection, and the safety factor. This is the element comparison, all on the same R5 geometry. Look at the linear tetrahedron here in the first row. It gives only just 90 megapascal and only 0.2 millimeter. Both numbers are far too low because the linear tetrahedron are overly stiff in bending. The quadratic tetrahedron and the hexahedron agree very well about 132 megapascal and 0.3 39 0.39. The lesson is that you cannot use the linear tetrahedron for this kind of bending problem. I used quadratic tetrahedron elements from here on. To trust the stress, I ran a convergence study on the R5 geometry, refining the mesh from about 2,000 up to over 500,000 nodes. The relative change meshes is the formula at the top here. As the two charts show, the both peak stress and the deflection flatten out quickly beyond about 20,000 nodes. and the change is under 1%, under 1% here. And the peak stress converges to about 100 and 132 megapascal, and I adopt the M6 mesh around uh 86 nodes, 86,000 nodes, because it is within the 10th of the percent of the finest mesh at the fraction of the cost. Before the comparison, two definitions here I will tell you. The peak von Mises stress always sits at the inner fillet. As the contour shows, the factor of safety is yield strength 250 megapascal divided that peak stress. And to compare the designs, I measured the stress reduction relative to the sharpest case R2. With these two simple measures, the four cases can be compared directly. And here's the comparison. Here's the results for the four fillet radii, all on the M6 mesh. Reading down the table, as the radius grows from 2 to 50 millimeters, the peak stress fall from 0. The peak stress fall from 177 down to 97 megapascal of a 45% reduction, and the deflection also drops from 0.41 to 0.32 millimeter, and the factor of safety climbs from 1.4 to 2.6. The deformation plots below shows the same thing visually. The bracket deflects as less as the fillet gets larger. These two charts summarize these trends. On the left, both peak stress and the deflection fall steadily as the radius increase. On the right, the factor of safety rises from 1.4 to 2.6. And two things to notice. The biggest single improvement is from R2 to R5, about 25%. And after that, the gains get smaller. So they are diminishing returns. And every case stays above a safety factor of 1, so none of them yield under this load. To conclude, increasing the fillet radius clearly strengthens the bracket. The peak stress drops by 45% and the deflection goes down as well. The factor of safety improves from 1.4 to 2.6, and the R5, R30, R55, R15, R15 is the best of the four. Two supporting points. The element studies showed that linear tetrahedron cannot acceptable here, while the quadratic tetrahedron and the hexahedron elements agree. The convergence study confirmed the stress is meshed converged, so the number are trustworthy. Here's the outlook and the future work. A few directions for future work. The most important is fatigue. Since the fillet is where cracks would start, a cyclic loading study would be the natural next step. Beyond that, optimize the radius for the minimum weight at a chosen safety factor. Run a nonlinear check on that sharpest case to confirm no local yielding. Model the bottom joint with preload and contact instead of a perfect fixed support. Use modeling, submodeling at the fillet for finer. Uh, Look at the local stress yield. Thank you for listening.